Okay, so this week we'll do the topology of orbifolds here. So basically, we do some introduction, different, basically cover the differentiable structures on orbifold and the triangulation of orbifolds. Okay, so we'll cover the triangulation of stratified spaces and then do the orbifolds as a consequence. So basically, we do the smooth structure, fiber bundle, Riemannian metric, and Gaussian-Bonnet theorem, and triangulation of vectors. Okay, so those are the three important topics here. So some references. So this is Satake's first paper introducing the orbifold, but I guess he doesn't do the orientation reversing case here. So a little bit. And the Gauss Bonnet. So this is the first what he did for the Gauss Bonnet theorem for the orbifolds. And the Thurston did orbifolds and hyperspace in chapter 5 of his notes. And here I think he first introduced non-orientable orbifolds here. And then this book is a fairly good book, Orbifold String Topology, Cambridge University, so done by Adam. So if you can get a chance to look at it, please look at it. But this is not essential. Uh, but for the group point of view, this is the book to look at. And and then chapter 13 of the Radcliffe book also has all reports. In it, okay. And this is a book by Bryson Hapliger, and so they also introduced what's called OV space. So this is a polytope with some sort of singular orbifold type structures, which is also useful in some sense. Uh, and then maybe Kato had this old paper of uniformization of orbifolds, and these are all papers and more basic. So this is a fairly rigorous, good paper here, and then they do these kind of things. So it's useful to look at these papers by more basic. Okay, so actually, he's from Netherlands, so so there are lots of people in Netherlands doing mathematics also. Um, Yeah, and then okay, so 내가 또 뒤로 갔는데 앞으로 가야 되는데 왜 이렇게 된 거야? 자꾸 뒤로 가냐고요? 이게 안 보여갖고 예. 그리고 and then this is my paper. It talks about geometric structures on orbifolds here, so it could be useful. So and Perona, so this is in LNM, and it talks about the triangulability of stratified spaces. And the Weinberger, this is also a very good book on the stratified spaces, talking about lots of different topics also. Okay, so let's go to the differentiable structures on orbifold. So suppose we are given smooth structures on each of these model space, and so U tilde is given a smooth structure, and G is also a smooth action on it, then we assume that all the embeddings in the atlas are smooth, and M is given a smooth structure. So that's the smooth structure on M. Or the smooth structure is sort of a maximal collection of those type of atlases which are compatible. And so given a chart, space of smooth form on it is the space of smooth form on U tilde invariant under the G action. So for each chart you can define this smooth form. So so the smooth form on the orbifold itself is you can think of it as a collection of smooth forms on each of these charts. So that on the embeddings they match up. Okay, so that's the only thing that they require. So match up means that they are consistently defined, right? So they transform according to the rule. Uh, so this is a sort of a more kind of a categorical way of doing things, but it's I mean it's completely set theoretical anyway. So we can define integral of a smooth single simplices into charts, and then this can be extended to any smooth simplex using the partition of unity and the barycentric subdivision of the simplices and so on. Uh, sorry, this should be B here. Sorry. So you can define integral just as in the manifolds for simplices or singular simplices and singular chain complexes and those kind of things. So given a locally finite covering of X, then we can define the smooth partition unity in the same way as in the manifold case. So of course here I have to tell you what the smooth functions are. So the smooth functions are the ones which lead to smooth functions on each model space, right? A model chart. And then so the point is you can also define these regardless where there's a singularity or not, the partition unity also exists. So the argument is very similar to the ordinary case, but you just have to make it invariant under the group G, okay, uh, and then you have to make sure that you sum up to always positive function, and then you have to divide by that function, okay, then you get a partition unity. And so the idea is to obtain a cover whose cover closures are invariant compact subsets, and so on each chart which vanish outside some invariant compact subsets, and the images of compact set can be chosen to cover X, and then so these functions become functions on which we can sum up to always positive valued function, and then we divide by the sum. Okay, so that's how you obtain the partition unity in this case. So the argument is very similar. You just need some invariance here. Okay. So for invariance, we just have to take this is a finite group. You have to just take the image and then you just have to average them together to get a function which is invariant. Okay. So this is a finite group. So. And also, orbifold is orientable if you can choose an atlas of charts where U tilde is given orientation with G acting orientation preserving manner, and each embedding to chart to another chart is orientation preserving. Okay, so you need to choose some sub atlas which satisfy this property, which preserves all the orientation here. So you'll have to exclude some things which doesn't preserve the orientation. So it will be not the original maximal smooth charts, but it will be smaller actually. But you can still obtain a maximal atlas like this, which are always orientation preserving. So any n function also can be integrated on oriented orbifold. So you have any set chart for U, then so this is a W prime is a chart form on U, which means it comes from some form U. I mean comes from some form omega on U tilde I. Okay, so then you integrate over there, and then the um, sorry, I think this 1 over G has to go to here, right? Sorry, this is a mistake. Yeah, sorry about that. Okay. So then any n form can be integrated using a partition of unity, right? Because once you have a partition of unity, you multiply by the n form, and then you integrate over all the charts, and then you take the sum. Okay, so that will give you the So that's exactly the same way the works for the smooth manifold. Okay, okay. Also, you can do Poincare duality pairing. So any compact orbifold without boundary. So which means that the boundary is there's no point modeled on the upper half space. Okay, so that's the case. So usually you call that the closed orbifold, and then if you can always do this kind of thing, HPX times tensor to the HNPQC over S. So this means it's compact supported, and then you get an answer here. So I don't think compact needed here because I have C here. But it is non-degenerate if you have a finite good cover. Okay, so then for the cross orbifold you get a non-degenerate answer. Okay, so that has to be proven, of course. Yeah. So the cover is of an orbifold is good if each U is of form Rn G, and all of its intersection is also of the Rn G. So which means that it's just a cell divided by some group. So in this case, standard differentiable form argument work, and the compact orbifold has a finite good cover here. So so cover here means that not the orbifold cover, it's just open set cover here. So that's the definition. So I guess you can drop the compact here. So that's a little bit confusing. Okay. Also, you can define the bundles over OV4. So an OV4 bundle or V bundle, E over an OV4 X is given by a smooth OV4 E, and the smooth map pi E goes to X. Okay. So that F is a smooth manifold with the group G acting on it smoothly. And then pair of a defining family of for X and F prime of X, so that U X G phi of X. So this is a OV model for X, and then U star G star phi star for where U star is U times F, and then pi star is equal to pi of circle pi. Okay, so this and so given these two and then another pair, there is a corresponding embedding. So suppose this for X there is an embedding here. Then it also goes to induces this embedding where where lambda star PQ is lambda P, and then G lambda P Q for PQ in U star, which is U times F, with the G lambda P is in G. So it will act by some element of G here. So the group G is acting. So this G and this G is of course different G here. And so we have this, suppose we have this property for these three embeddings. So if you have one embedding and then going to another embedding, so if you have two embeddings, and then you can also have this property. Okay, so that this is the only for bundle. So if you have these kind of properties, then you say this is a OV4. So I defined it using the left action here, right? And but of course you can do it in the right action as well. But you can also multiply this on the right. But here F is acting on the left, so I'm doing that here. Okay. So when F is C, and then if I use the right action, then I guess you can get the, or you can just use the left action. You get a principal OV4 bundle. Okay. So so then So then you'll have a right action. If I define with the left action here, then I can have a right action and so on. So if I for f itself, I don't. I think that there will be right action if I define it like this. So this is a so in that case it will be principal orbifold bundle. So that's a generalization of a bundle to the orbifolds cases. Okay. So we can actually, given an orbifold, we can build a tangent orbifold bundle by taking the F to be Rn and G to be GLN and the G lambda P to be the Jacobian of lambda P. So if I go back to here, so suppose we have these, we have these data, and then you build these things with F, and then so we have we can use the Jacobian matrix for each transition function, and then you can build a tangent bundle this way. And any tensor bundle can also be built this way. Okay, so tensor bundle, you just have to choose F to be the tensor over Rn, so some RS tensor, and then G will act on this, and then of course the Jacobian will act naturally on this. So you can do the same thing here. So frame bundles, of course, then F will be the space of frames on Rn, and then the Jacobian will act on the frames in the natural way. Okay. Uh, and also the Riemannian metric on orbifold is given by equivariant Riemannian metric on each chart, which match up on the embeddings also. Okay, so you can always do that. And then so such one can be built by partition immunity again from any. So you have any given Riemannian metric on each chart, then you can use the partition immunity to sum these up together. Okay, then give you a Riemannian metric. And also orthogonal frame can be built this way. So once you have a Riemannian metric, then you can require F to be the orthogonal frames. Okay, space. And then you can so here G will be the orthogonal group, and then it will be built like this. So once you have these bundles, then you can define connections, curvature, geodesics, and exponential map. So because these are all local constructions, so once you know the model space, how it works, then you know everywhere it works. Okay, you just need some equivariance to do this. So everything works. And so for the Gauss-Bonnet theorem, so assume that X admits a finite smooth triangulation, so that interior of each cell lies in the singularity with the constant isotropic groups. So you can we'll show that this can be done. Okay, so each singularity is in some sort of a locally constant isotropic group. Each cell lies in some singularities. Okay, so of course the singular isotropic group could be trivial, right? Then we can define the Euler characteristic to be the sum of dimension Sk. So Sk is the cell, K cell, and then 1 over NSK is the order of the isotropic group. So for each cell, you add up these numbers together. Okay, so that's the orbifold Euler characteristic, and so this is always exists. So we'll show that a little later, and then so for M compact Riemannian orbifold of even dimension M, then you can obtain this formula that the Euler characteristic is the so some integral of the curvature. So this is a tensor coming from the curvature, right? So for dimension 2, it will just be the curvature, a scalar curvature, but in other things it won't be, right? So this just follows from the same proof as the Chern's proof of the Riemannian manifolds. Okay, so